Okay, now I'm actually talking. Yes, I mean, I'm muting myself there. Sorry. I had another student that was in here in person, so I thought it would be better for him if we actually went in what he wanted to do, and then we can go over some of the ones I think a student put on the Schoology group that she wanted to go through these, and I can go through some of these. But just for FYI, there's another video that's going to be up that are over problems 52. We talked a little bit about 57 a little bit. So this is my work here. 52, 57 a little bit there. We did a tension problem. Where's that work I just did? So we did a tension problem that consists of basically number 64. So I write out the work for here. And where is that? Oh yeah, it's on this side here where we find the acceleration. It looks really confusing, but watch the video. That student felt very confident going out of there, so hopefully it helps you as well. Don't just use it as like, hey, I'm just going to pause it and write down exactly what you have, because that's not going to help you at all, because there's other problems that that if you can solve. For example, if you can do 52, which is that block on a block, or the beams on a truck one, if you can really understand this one, I just wrote bigger here, then that sets you up for solving basically the next 3 or 4 problems, even the inclined plane problem. So today we're going to be looking at or this video. Try to find the paper that the student wrote those things on. The suggested problems are 22, 26, 29, 33, and 38. I was thinking that I might also do this Zoom thing on Wednesday. We usually have our PLC meetings, but we don't because of parent-teacher conference nights. I have to be here anyway. I think my first meeting starts at 4:30, so at least we can just talk about some last little tips and tricks and things like that. But I'll probably have another one on Wednesday for that. So let's go ahead and start with here. What my goal is here is to in helping you with this is kind of like when I see a problem, you know, instead of kind of like, oh, what is trying to figure out what is the content? What, like, is it, are they asking, am I having to think linear motion? Am I having to think friction? Am I having to think of Newton's laws in terms of first, second, or third? That's sort of my help there. So let me get my papers here in order. Had to mix them all up here. Blue, orange, purple, they're all color coded. As of now, these are the problems here, and I have a few problems here that I'm kind of in the mix of solving here, but if you get to this point right here, which I believe is number 70, that the ones after that are just additional problems, and you can see they basically consist of the blue ones and then the red ones. I haven't looked at the red ones yet, so that's sort of the goal. If if you can get through all the problems up to the additional problems, you should have enough with maybe a little bit of help to get through those. So depending on what you want to go through on Wednesday, I may go over those additional problems because that might be more akin to what you would have on an AP Physics exam or test. So let's look at this. I do have my book here, so I'll show you which one's here. Okay, so 22 is, let me go ahead and refocus my camera here. So the first thing I see when I see 22, first of all, if it ever says review here, you have to think, what was the unit you just did before, which was 2D motion or linear motion, and you're most likely going to be using that. So let's read through. It says, 3 forces acting on an object are given by this, this, and this. The object experienced an acceleration of magnitude 3.75 meters per second squared. So that's the acceleration. What is the direction of the acceleration? And what is the mass of the object? And what is if the object is initially at rest, what is its speed after 10 seconds? That's basically a linear motion, constant acceleration problem. And then what are the velocity components of the objects? That right there is basically using cosine and sine to split it up into your x and y components. So when I look at this right here, and they're wanting to, first of all, if they're talking about acceleration, and they're talking about, when they're talking about finding mass here, and they give you acceleration and they give you forces here, that definitely is probably leading to find that mass, you are going to use Newton's second law. So, but we can't use all these individual forces apart. We need somehow a way to add all of these vectors together into a final magnitude and direction. That's called vector addition. And once we have that, we can divide it by 3.75, and that's how we find what the mass is. So also, when they're asking about the direction here, so in our class, or I mean in pre-AP physics, we had like a problem. We had a quiz where you had to like do this, I think it went like that, it went like that, or something like that, and that. And you had to figure out the x hats and the y hats of all those components. You had to add up all the x hats, add up all the y hats, do the Pythagorean theorem, do the inverse tangent, and maybe coming back to some of you of Vy over Vx. This is what we have to do. Now, we don't have to split it up into its x and y components. We don't have to do the cosine and sine because they already give us the direction here. We have to remember that I, for this case of here, that I is basically the equivalent of what we did in my class as x hat. It's the it's how much in the x direction. So, and then j is representative y hat. And if we had a third dimension, we'd have k, and that would be the z direction. But we've never done that, so we don't have to worry about that. So if that helps to kind of understand that this is telling you how far right or left, and this is telling you how far up and down. So let's go ahead and write these forces here. And I'm actually going to stack them up in a similar manner. So I'll just write them down here from what they're. I'm going to write it in a similar manner. From our class, we wrote it like something like that, x hat plus like that y hat. But this is a shorthand version. So let's go ahead and write out F1 is negative 2i. And I like writing my i's like that because, I don't know, if I write an I like that, I can just as easily maybe write it like that, and now it looks like a J. So I want to make sure I definitely don't write it that way, so I'm basically writing a backwards J. So I know that that is an I. I'm deliberately doing that. So minus 2i, or negative 2i plus 2j. So what that's saying is that it's saying it's going to the left and that it's going up because it's negative to the left and positive up. And for F2, we have 5i minus 3j, and this means that it's going to the right, and this means it's going down, just to let you know kind of what's going on here. And then the last one we have here, even though it doesn't have a j, I'm still going to put a placeholder there, so it's negative 45i. And it doesn't have a j, but just to make it easier, just do 0j, just so we know what we're doing here. And we're adding all those vectors up. It's basically you have like some object here. Sorry, this is to the left. You have some object where you have like F1 is somewhere over here based on left and up. F2 is somewhere in the fourth quadrant here because it's right and down. And then this is completely to the left. So you're trying to figure out like what overall force, and it's most likely, if I look at my numbers here, hold on, what that should actually be. Oh yeah, it ends up that it's actually really close to being just directly left. So we're trying to figure out what is that. Once we have that, we plug it into F equals ma. We know F, they tell us A, and we solve for M. Okay. So first, let's go ahead and solve for all of our forces or our resultant force. So we have negative 2 plus 5 plus negative 45. And when we do that, we get negative 42 I. Okay, 2 minus 3 plus 0 is negative 1j. So once again, what that's telling us is that it's going to the, it's not going to be there. It's going to be a little bit below there. How we know that is negative 42i is saying to the left, and that is saying down. I am going to make an angle prediction here. And so that means it's going to be left and down, which means it should be somewhere in the third quadrant. Then I'll go over angle correction if you need that. Now that we've done that, all that we do, so to figure out the magnitude, we use the Pythagorean theorem. To figure out the angle, we figure out the inverse tangent. So they're asking us, first, what is the direction of the acceleration? So we can actually figure that out first if we want to do part A first. So what is the direction? We'll do the inverse tangent. Make sure your calculators are in degrees. We're not yet doing radians. So it is the y component over the x. This is the y, so -1 divided by -42. Yeah. And let me go ahead and just double check that with my calculator. I'm kind of looking over at my notes here. Inverse tangent, -1 divided by -42 is 1.36 degrees. I'm like, oh yeah, that's exactly what I should get. However, we're coming into the angle correction. Your calculator, remember, can only give you answers in the first and the fourth quadrant. 1.36 seconds is somewhere over here. So here's what my prediction said. Here's what my calculator said. And whenever they're in opposite quadrants, you add 180 degrees to that. Maybe I shouldn't draw an arrow. Maybe I'll make a little wiggly so you know it's not part of that. And that ends up, it ends up with 181.36 degrees. That is our angle. Okay. So these forces here, and it kind of makes sense here because you have a force that's up and to the left and down and to the right and completely left. And so what it looks like here is these almost completely cancel out. So that we have this thing going to the left, because 181.36. Remember, that is basically somewhere over here. Okay, so that's the direction. To find the acceleration, this is the difference between whether this is a black numbered one or blue numbered one. I feel like in a black numbered one, they would just say what's the force, and then ask you what's the acceleration. But they're kind of making you realize that this is a two-step problem. So we need to take this right here and do the Pythagorean theorem with it. So F is the square root of -42 squared. Make sure in your calculators that you are aware that if you don't use parentheses here, if you do -10 squared in your calculator will give you -100 because it thinks you mean this for some reason. And so how you avoid that? Do that. Or another strategy is if you know this is supposed to be a positive number, just do 42 squared plus 1 squared. And F ends up being, I'll go ahead and double check that, 42 squared plus 1 squared, square root that number, 42.01. And there may be different ways of rounding. The book might just say, hey, the answer is 42. I'm just giving the way I would do it here. So that's the force. That's not the answer. We now plug it into Newton's second law. A equals F over M. That is 42.01. And the mass, what was the mass? They said the mass was, oh, I'm sorry. We're finding the mass. Sorry. Thinking about the last problem. We are finding the mass. So that means M is F over A. So that's 42.01 newtons. Divided by the acceleration, which is 3.75. Oh, my light's gone off there, 3.75. And when we plug that into the calculator, we get 11.20 kilograms. I'm going to take a break here just and see what in the world just happened there, okay? So you're like, well, if I'm looking at this, how do I know that we're going to be doing this here? So because there are other problems that we had, and we're not done. There are other problems that we had where let's see here. Okay. There are other problems that we had before where it was giving you this I and J, but it was telling you your velocity or your displacement or your acceleration here. The fact that these are all forces, they're all the same thing. and they're telling you the acceleration, and you have force, and they're asking you the mass. You're thinking F equals ma. And how I knew that we had to do vector addition here is that we have 3 forces, but we need to know what the overall force is, and that is a clear identification that that is a vector addition problem. So back to where we are over here. So once again, this is just a vector addition problem as you set it up. If you forget how to do vector addition, actually I just showed you here, but if you want more of that, I have videos on my YouTube page. My YouTube page is very creatively Kevin Dahlstrom. You'll know what it looks like because it's a picture of my face when I was in high school, like over a drum set, something like that, like a drum set. Things are here and there like that. So yes, good enough. It's also the only one, if you click on it, that actually has videos for me, which also makes sense. And it has the most subscribers, so we're making a dent with our 27 subscribers. So let's finish the problem here. They say, if the object is initially at rest, what is its speed after 10 seconds? This is a linear motion problem here where we have, we know the acceleration, that's 3.75. They're giving us a time of 10 seconds. If they say it's initially at rest, so VI or V naught, however you use it, is 0 meters per second. And we are wanting to know, what is its speed? Oh, that's an easy one. So if I was doing that one here, I know it's not the same way you write it in your class, but this would be my second equation, which is VF equals VI plus AT. VF equals 0 plus 3.75 times 10, which is 37.5 meters per second. A lot of these problems are, I've noticed, especially the blue ones, they're upfront heavy, meaning that you may be doing a lot of work in the beginning. But for example, we did a lot of work to get to this force, but once we had that, we find the acceleration, we find that, so it's not always so serious. And then what are the velocity components of the object after 10 seconds? So here's the thing, you're like, what's going on? Let's go back to sort of what's happening with our picture here. We have this block that we know is basically moving in this direction. The angle is 181.36, and it, because we figured out the acceleration of the direction of the accelerations. This whole thing is moving this way. We know the acceleration is 3.75 meters per second squared. That actually won't necessarily help us with this. And we have the final velocity is 37.5. So what they're asking here is not what the speed is. This is the speed. They want to know, basically, let's see where my colored pencils are. There's one here. We want to figure out what is that component, what is the x component of that, and what is the y component of that. And how we do that is we use x was going to be cosine for this one, and y is sine, or I guess if I write the equations how I did last year, at least in pre-AP physics, that means our velocity in the x direction is v cosine theta, and v is their vector, and the velocity in the y direction is v sine theta. So your Vx is going to be 37.5 cosine 181.6. So V is 37.5. Theta is 181.36. Making sure that you're in degrees. And when you do that, you get a Vx of, let me just go ahead and double check. 37.5 cosine. If I can do this, 37.5 cosine 181.36, 7.5 sine 181.36. And let me double check what I had here. Yep, okay, so for Vx we should get, hold on here. Oh yeah, okay, we should get negative 37.5 0.49 meters per second. You're saying, well, does negative make sense? Well, yeah, it is moving to the left. This should be a negative number, and so should Vy because it is also moving down, and Vy comes out to a small negative 0.89. That should also be negative. You may be wondering, isn't that a pretty small number here? The reason is that this thing is basically moving completely sideways. This is almost completely to the left. However, it's a little bit below into the third quadrant there. So our triangle is more like something like this, where I'm trying, like this is 37.5, our x component is that, and then our y component is just this little tiny bit right here, which is why that's such a small little tiny number. So that wraps up 22. Wow, that is a doozy. That took 30 minutes. Not necessarily take their 30 minutes for the instruction there, but we can be happy because that is a blue one. And any blue ones you can get off there. Let me look at some other ones here. Okay, 26 honestly took me more time than I needed there. I almost had a little bit of brain fart and what's kind of going on there. Moving on to 26. So here's my work for 26. I didn't know how much room it would actually take me. There's my room for 22. So it is possible to do 22 with taking less. So here I found the Pythagorean theorem, did the inverse tangent, found the mass, plugged it into the second equation, found the velocity, did the x and y components, and got that. So I just didn't draw as much. So you can certainly do that, but never try to box yourself in. I didn't give myself this space. I technically gave myself the rest of the paper to do. I just realized that I could do that. So however you do it, don't box yourself in. If you feel like, hey, I'm not going to have enough room, draw yourself a big old box. And because it's very stressful if you're trying to do a problem like that in 3 lines. Okay, 26. Which is this the one where the magnet is pulling it? I think it. Yeah. Okay. It's like, is this really okay? An iron bolt of mass 65 grams hangs from a string, so it's basically hanging from a string there. 35.7 centimeters long. The top end of the string is fixed, so it's being held. They're sort of like a pendulum. Without touching it, a magnet attracts the bolt. So let's say that this is the bolt at the bottom. There's a magnet that comes along, very similar to my magnet right here, and is causing this thing while it's hanging to start to pull over to the right side there, okay? So that's the force. So what's the force going on? The magnet is pulling this. It'd be the same if you were taking this and holding this back, but the force of the magnet is what's keeping that on. So yes, reading that, you're like, what is going on there? It says that, so magnet attracts the bolt so it remains stationary, okay? So that's good. Stationary is very, very helpful for us because that means that the sum of the forces are going to equal 0. It is a balanced force. If it was accelerating, that would be quite a different little story there. So that would be a blue problem or a red problem. So it's stationary, it's balanced, and that means the sum of all the forces are going to be equal 0. But it is displaced horizontally 28 centimeters to the right from where? So basically the distance there is 28 centimeters. The magnet is located to the right of the bolt and on the same vertical level as the bolt in the final configuration. Okay, so what that really means is that the magnet is going to be pulling. Sorry, I'm slowing this up now. Is that the magnet is at the same here, which means that your force is going to be directly to the right. It wouldn't be the same like if the magnet was up here, then the force would be there, the force would be there. It's saying it's literally right there. So your force at that point for the magnet is straight sideways, which is helpful, which is straight to the right. Draw a free body diagram of the bolts and find the tension in the string and find the magnetic force on the bolt. This is a really, really long way of just saying, of just drawing basically this. So in this problem here, if we say that that's the, move that back. If that's the surface where this thing's connected to, we have where the original bolt would be there, but now it's being, it's over here, so it's like that. They're telling you that this distance right there is 28 centimeters or 0.28 meters. they're telling you that you have this magnet right here that's pulling it completely to the right. And we're having to figure out what is the tension here for that. Let me go ahead and refer to my notes right here real quick. Okay. Let's see here. Okay, so let's go ahead and draw our free body diagram, and we're concentrated on this. So this is another one where we're kind of drawing a little bit of box around that can kind of make it, oh, okay, there's not really that much going on. You have your tension, which I'll redraw this again. You have your tension over here. You have the force of the magnet this way. And then you have the force of gravity straight down. And that's all you have. So let me redraw what that looks like. So you have your bolt. You have the force of the magnet there. You have your tension there, and you have, oops, you have your force of gravity, which is really just M times G. Okay. And we have to figure out what this angle is here. That's the crucial thing of figuring out whatever that angle is. And this is the part that I was just, for some reason, was just taking real long to do. I was struggling with kind of, do I have to take into account this this angle here? And no, you don't. Meaning that here's where the original bolt was. It's now over here, but whether the bolt is here, we can just basically extend this triangle here. If this is where the bolt is, we know that this is 0.28. They tell us the length of the string is 35.7 centimeters. So we know that the original length, this is 0.357. And so we can now figure out what that angle is right there. Hold on, did I figure out that angle? Oh, let's go ahead and, yeah, we'll figure out this angle, then we can figure out the other angle. So we'll figure out what that angle is right there. And we can use sine because we're doing opposite over it, or is it, so tangent or sine? Let me see here. Hold on here. Trying to see the way that I had solved it there. I'll have to check my work. I'll have to check my work when I have it there. So 0.357, sorry, this would be tangent. So similar to the last problem, we're going to use the inverse tangent of the y over x to figure out what that is. So or just tangent theta is 0.357 divided by 0.28. Run out of space here. And we get an angle of about 51.89. Okay, so that's what that is right there. So we now know this. Come back to that later. Also, so you're saying, okay, well, yes, maybe I'll draw a free body diagram, but I have absolutely nowhere. So whenever you have a free body diagram and you have forces going in different directions, it's not a vector addition one. It's not a vector addition because we don't know we know what this is, but we don't know what that is. We don't know what that is. So this is the one where you're doing, at least in my class, and I will do this here, where the sum of the forces in the x direction are right minus left equals ma, and the sum of the forces in the y direction are up minus down equals, hold on here, sorry. It will be, oh, sorry, yeah, ma as well. But because this is stationary, it said it was stationary, that means that the acceleration is going to be 0. So for this one, both of that is 0, and both of that is 0 as well. So let's go ahead and do the sum of the forces in the x direction. Sorry, I'm looking this and I found an error in my notes and I need to go back and fix it. It is an even one. And I was like, oh, okay. So the sum of the forces here, right minus left. So right, we have the force of the magnet minus the minus t, but it's going to be t. See whether I want to use this here. I want to go ahead and figure this out here. We have two components of this. Okay, we have t in the x direction, and we have t in the y direction. Okay, and so if this is the angle that we're given here, the little trick that I was telling my other class here, and you may remember it from previous years, maybe not. Another scrap piece of paper. That if you have some angle here, so let's just say for this direction, it's this is your vector in the x direction, this is your vector in the y direction, then that's the actual vector. If your angle's here, how do you know if you're using cosine or sine here? It's really corny. I think Ms. Ward-Prem uses it as well. So this theta is connected to v of x. So that means that v of x is going to be v cosine theta. But even in ones we'll look at later where we have a free body diagram where if that's an inclined plane, that's f of g. We have our fg of y, and we have our fg of x. And the angle that we're given is this angle right there. And in this case, the angle is connected from the hypotenuse to fg of y. So that means for that fg of y would be f of g, cosine theta. That's how you know, whatever one's connected to. So we look at over here that t of x is connected to the theta. So that means that the t of x is going to get the cosine. So we'll do f of m minus t of x equals 0. Okay, or f of m is minus t cosine theta equals 0. Just make a double check here. Sorry. Ugh. It's a long day. It's mousetrap card day, so sorry if I'm making a little bit of mistakes here. F of the magnets. I have normal force on my mind from the last video here, so apologies there. So that's all we know, and we don't really have enough to solve for that right here. And you're saying, well, how is that going to help us here? Well, what they're asking us here is they're saying, draw a free body diagram, find the tension in the string. So we're actually going to do it. There's not enough information in this x direction, so that means we have to look in the other direction. Once we find tension, we'll know tension, we'll know theta, and we can find the force of the magnet. So let's, once again, if there's not enough in this direction, we'll save that for later, and we'll look in the y direction for that. Okay, so in the y direction, we have up, which is t of y, minus force of gravity. I'll write it out. Force of gravity equals 0. If t of x was t cosine theta, it means t of y is t sine theta minus mg equals 0. And this is helpful because we know theta, and we know the mass, and we know what gravity is. So let's go ahead and solve for that. T sine of, what do we find? Was it 51.89? Minus, what's the mass? Mass is 65 grams. Careful here, not so 65 grams. Divide that by 1,000. It's 0.065 kilograms. That's what we need to be in. Minus 0.065 kilograms times 9.8 equals 0. Go ahead and plug that in. So 65 times 9.8 divided by sine of 51.89. Oh, that's not a sine. Let me confirm with what I have over here. And I got 0.81 for my, let me go ahead and double check here. Yeah, 0.81 newtons. Okay. Let me just go ahead and double check my work here. So yeah, with f of m minus t of x, we were using t cosine theta which we had here. We had T of y up minus the force of gravity. T of y was T sine theta. Also double check on my angle here. So they told us that that distance, because no matter how long we stretch this here, that is always going to be the same theta. They told us that the original length here was 0.357. They said that the distance from here to this line here is 0.28. Opposite over adjacent, TOA is tangent, so tangent of theta is opposite over adjacent. To find that, I did the inverse tangent of both of that right there. Got 51.89. Plugged it into here, got 0.81 newtons. Now this goes up here. So we have the force of the magnet minus 0.81 cosine of 51.89. And that means 0 means F of M is 0.4999, so 0.50 newtons. Okay. And let's even ask ourselves, does this make sense that the tension should be more than the magnet here? If the bolt here, if was somehow like, you know, the magnet was pulling it this way and the tension were pulling it that way, then that means that the tension and the magnet would be the same. But that's not what the case is here. It's actually pulling up here, and we're only getting a small component of that force there. So once again, if they were opposite directions, these would be exactly the same. So it makes sense that this right here would be a smaller number than that right there, because we're having to take 0.81 times the cosine of that angle rather than just doing cosine of 0 for there. So that at least makes sense in that case for that. So that wraps up number 26. So that's the cable one there. And once again, how do we know? There was some words there. It told us this is stationary, which makes this problem much, much, much easier because everything equals to 0. However, what if this was accelerating and we knew the direction it was accelerating in or something like that, or that we had to find the acceleration? We would just have this M and A. They would have to provide us with more information in order to solve for that. So that's 22 and 26. At least these are sort of different types of problems. We'll see how much we have here. 29. It's a block versus a block. Where is my 29? Okay, let's see here. 29. It's that one. It looks complicated, but I'll show you a strategy that we used on our other video for when we were dealing with multi-block systems that we're just going to concentrate on individual ones as we go by here. So assume the 3 blocks portrayed in the figure move on a frictionless surface. The fact that this is a frictionless surface is the difference between this being a black numbered 1 and a blue numbered 1. So it actually makes it a little bit easier in having to solve this here. So let's see here. Moving a frictionless surface and a 42 Newton force acts as shown on the 3 kilogram block. This is basically a train type of problem that we've done before. Determine the acceleration given this system and the tension in the cord connecting. So what's the tension basically right there? In the core connecting 3 kilogram or 1 kilogram blocks, and the force exerted by the 1 kilogram block on the 2 kilogram block there. So it seems like a whole lot at once. I try not to think about how I'm going to solve C before solving A. I mean, the book, they ask you to solve things in order, which is nice because it kind of helps you step along the line there. New paper. For 29, where we have this here, 29. The other goal for this is that these are all pretty different types of problems, where 22 was vector addition and remembering that. 26 was a free body diagram, sum of the forces, balanced forces, this one. 29 will help with your tension problems, but also will help understand Newton's third law here, because one of the things of understanding here is that the force that the 1 kilogram acts on the 2 is going to be the same as what 2 does to 1. They're reactionary forces here. So let's go ahead and draw our picture here. So this is 1 kilogram. This is 2 kilograms. There's a rope or a cable that is pulling this. I know it's not drawing the scale here. 3 kilograms, and we have a 42 Newton force in this direction. When you see all these different blocks at once, I like to kind of think about this as I'm going to first separate. I'm going to treat this like a train problem to figure out the acceleration and the tension. Although we have 3 blocks here, and if there's no friction, we can really think of this as these are one block themselves. So you just add their masses up, okay? And this is the other block that we have. And the reason for doing that and separating it here is that we can concentrate one at a time. We can say that there's a force to the right on 3. That's 42 newtons. There is a force back this way, which is T. That's all we have. Yes, there's forces that are up and down. I'll go ahead and draw them as well. You'd have the normal force here and the force of gravity. Why why can I just disregard this here? If frictionless, here's a kind of a helpful time saver. If it's frictionless here, then some of the forces in the y direction are just going to equal 0. Assuming that so frictionless, sorry, flat surface. If it ends up being an inclined plane, it's a little bit more. It's more complicated than that. So on a flat surface, if it's frictionless, you can say that some of the forces are 0. The reason being that if I have another, let me go back to another paper here. Ones that are a little bit later on. Hold on. Papers are all scattered. Let's see here. One that's like that. And here, hold on. Yeah, I know this is a lot of numbers here, but this is basically that. If f of n up equals force of gravity down at 0, so f of n is equal to mg, your f of n here it comes from this equation over here. So sorry, it's 0 minus force of friction equals ma. F of f equals negative ma. Using this equation up here, I know a lot, you can pause this many times. Using this equation up here and solving for force of friction, you get mu n, which is that. And that's what f of n is there. But we just figured out over here that f of n is also mg. So you can plug those two together. And it's a really long way of saying that if there's no friction, okay, so you can follow this. Yes, this is negative. The only reason it's negative here is because it's slowing down. But you can simplify, and I'm not necessarily going to do it here, but you can simplify your acceleration here. I'm gonna hold off talking about that. I don't want to get too confusing. We'll go over that problem in due time here. But what I'm saying is that if f of n equals f of g and there's no friction here, there's no reason to use the y direction. So although there's normal forces and there's force of gravity on that, and there's normal forces and there's force of gravity in that, this block has sorry, let me use my pencil. This block here has tension. Get all my papers organized here. Color coded them all. And that's just the force I'm going to draw. You're saying, well, don't we have to figure out the force between them? We'll do that afterward. We're treating these like similar blocks. Afterward, we'll figure out what the forces are on them here. Okay, so See here, we're going to go ahead and write an equation for the mass 3. Okay, for mass equals 3 kilograms. So once again, the sum of the force in the y direction, I'm not even going to worry about drawing that because it's frictionless. We have the sum of the forces in the x direction here is right minus left. So I have 42. Check here. Yeah, 42 minus t equals ma. And the m here is 3. So 3a. I'll rearrange that to solve for tension. Okay, so I move tension over here, subtract 3a, so 42 minus 3a. We don't know acceleration, we don't know time, but we're going to come back to that. It's going to be helpful here. The whole reason here is that we know that these two tensions are exactly the same because they're the same exact cable. You can't have more force on one side of the cable than the other. So that's the trick there, knowing that the tension are exactly the same. Now let's look at the other system here. So this is the mass of, let me see here. Yeah, this is the mass of the 1 plus 2, which also ends up being 3 kilograms. So in this one, we have, there's no friction, so there's nothing pulling back. We just have the sum of the forces to the right. We just have tension to the right, nothing to the left, equals the mass and the mass of the combined ones, which is 1 and 2, which is 3, and this equals 3a. Okay, so t equals 3a. Make sure I got this right here. Yeah, okay. So now that we have this and this, we can just set them equal to each other. So 42 minus 3a equals 3a. We add that over there. 42 equals 6a, and a equals 7 meters per second squared. Okay. Now, some of you might be realizing, hey, did we really have to do all that? And if we have these blocks in the system, you can notice that what we actually just did is we took the overall force acting on all of them divided by their combined masses here. So 1 plus 2 plus 3 is 6. 42 divided by 6 is 7 as well. I would still recommend practicing doing it this way because if there is friction, you cannot necessarily do this as easily. So especially if you have friction that's different on those. So we'll maybe look at some of those more difficult ones later. But that's the acceleration. What we're now trying to find, we'll try to wrap this one up here. May not get through all of them, but I am going to do another one on Wednesday after school. So what are we asking for? Sorry, I'm trying to figure out where we are. And the tension of the cord, and then the force exerted by the 1 kilogram on the 2 kilogram here. So this is something that I kind of struggle with, and it's always interesting to figure out like what things I need to work more on. But Newton's third law has always been sort of a kind of difficult one. So that's part A, that's part B, and then part C is figuring out the forces on that. Oh, sorry, we didn't figure out the tension. To figure out the tension, we need to plug it into there. So T is, sorry, that's not the, this is part B. T is equal to 3 times 7, which is 21. And you might be like, hey, you know, am I done there? Well, you should always check because these tensions should be the same. So you should be able to plug 7 in over here and get the same answer. So let's go ahead and check. T minus 40, sorry, equals 42 minus 3a. 42 minus 3 times 7, which is 21, and t equals 21. They are the same. Yay! We know we did a right answer there. If they aren't the same, there's some answer. That's also why writing these equations that allows you to solve for the tension there, based on the masses. Sorry. Now let's go to C, and C is basically now we're looking at these individual blocks. So we have block 1, and then we have block 2. And so for this one, kind of realizing that yes, these are individual boxes here. We're now actually going to split them up into their own sort of respective. It's like, well, that doesn't really help, but they're individual boxes as thinking them as one right here. Okay, we have to realize that there's forces here. There's going to be the force of 1 on 2, so the force of 1 on 2, force of 1 on 2, but that is going to be equal, because of Newton's third law, every action is equal and opposite reaction. That is exactly the same as the force of 2 on 1. Even though they have different masses, the force at the contact is the same. Okay, so really what we need to figure out is how, and we also have this tension we know that's 21 newtons, is how how hard they're pushing on each other at this moment here. So let's go ahead and let me go just review this very quick. This is the part I had to actually look up a little more online. I'll try to look at my notes here and figure out the best way to sort of explain what is going on here. Hold on. 1 + 2a 0. So let's set up our equation. We know that f1 of 2 equals f2 of 1. Okay. So what that means in this case, the whole thing is accelerating, but between these two here, the sum of the forces is going to equal 0. We know that that's what it's saying. We're basically saying that f1 of 2 minus f2 of 1 equals 0 at that point. Okay. And let's just look at one of the blocks right here. Let's look at f2 of here. f2 of 1. So f2 of 1 is to the left because it's pushing back to the left. Hold on here. Pause this real quick. Got an email. Okay, back. I had to refer to that there. That with these forces, you're saying, well, where are these forces coming from? They're coming from this acceleration that is going sideways here. So we know how much force is on this 21 newtons right there. But we're trying to figure out specifically how much is f2 of 1 pushing back on f1 of 2 here. So in my notes here, I have f2 of 1. The force of that is related to the mass. So using Newton's second law, okay, f2 of 1 is related to the mass of number 2, which is 2 times the acceleration. Okay. And if we know what the acceleration is, f2 of 1 here is equal to 2 times our acceleration up here, 7. Sorry if this is not as flushed out. I'll try to maybe update this here. So f2 of 1 equals 14 newtons, which is also what f1 of 2 is. Okay. So reason why are we looking at 2? Why are we not looking at 1 here? Because we know the force, the tension force on this that's acting on it. Instead, we're looking at the reactionary force of 2 here. So the force that they have in between them is related to how much this block has to be accelerated. Think about the 1 is being accelerated to the right. This is pushing this here. So the force between them is going to be related to how much this block has to push on this block here. So that's why it is the second mass. So 2 times 7 is 14 newtons, and that is the force in between that. So once again, if that's the confusing, I apologize. Did the best I could in short notice. That's something I had to look up. I'm going to wrap this up, but I'm going to say what I did for some of these problems, because once again, I'm still kind of learning, getting better, is that, a lot of places you have Chegg, you have Study, you have all these things that are going to pay. I have found that using physics forums is helpful. A lot of people don't necessarily know about it or think about it, but almost every single question has been asked there. It's more of a kind of a blog where somebody puts up a question and then some accredited professor or something will type back and give some more help. It may not be as flushed out or as easy to read as maybe Chegg or the other ones there, but it's free. And so that's actually helped me out a lot in trying to understand some of the more complex ones. So I know we only did 3 problems in an hour, but you're like, oh, it's going to take me 1 hour to do these. Not necessarily. I tried to explain it so that there was the theory behind it, because it's, yes, if you did the homework, great, but can you repeat it, or can you apply it to a question that is on the test? I think like I said, we didn't get through all of them I wanted to get through, but I do have another life outside of this. So the last ones we didn't get over are 33 and 38. And what I'm going to do here is I'm just going to show you what my solutions are there. And then if you have questions, this 33, I ran out of room. So you're like, oh my gosh, that's a lot going on there. But if you took some time to look at it, number 33 is actually similar to the magnet in the bolt one, where it is a stationary one. And if it's stationary here, the sum of the forces equals 0. So we know what this angle is here and this angle is here. So T2 cosine of 40, because we're figuring out the x component there, minus T1 cosine of 60, they tell us the angles here, by the way, equals 0. Then we can go up and down. So T2 sine of 40 plus T1 sine of 60. So they're both going up. Minus 325, which is what the force of gravity is there. Okay, you have that. We can simplify some of that with just basically plugging in some information that I have. Let's see where I got this from. To kind of break this down, it's been a while since I did this problem here. Oh, okay, I see what I did. Okay, so in this equation up here, I rearranged this top one to solve for T2, and I got T1 as cosine 60 divided by cosine 40. That ends up being T2 is 0.65 T1. That's a helpful thing, because in this equation right there, I substituted 0.65 T1, which is right there. That's where this is this right there, because I need an equation that has only one tension here. And if you think about it, we know everything except for T1, so you rearrange everything and you solve for T1, it's 253. Once we know what that is, we plug that back into here, or we plug it basically back into there to solve for T2, which is what I did, and I got 165 newtons. That is that one right there. So the only really kind of difficulty in here is understanding that you have your x and y component of that, and you have your x and y component of that. If it's sideways and you give you this angle, it's cosine. So cosine sine, right minus left, up minus down, everything equals 0, creating something here to plug into the other one. So I know that's a lot right there, but you can replay this many, many times as you want. And what was the other one we needed to do? I think it was 38. So which was 38? Find 38. Oop, maybe on this one. Should be on this one. Okay, 38. 38 was very frustrating for me. You can see that I tried to draw different diagrams and all that. And I wrote myself note, I made this way too complicated. I tried to solve all these different parts here. So I actually, after looking up how to do this, or what the answer was, pulleys are a way of just redirecting your forces. So you can simplify this whole thing right here as whatever this force is down here. They tell you in 38. So 38 looks like this problem right here. Okay. They tell you this is 8 kilograms. So 8 times 9.8, you can figure out the force of gravity. That's where that came in. Okay. So 8 times 9.81 or 9.8. So it's asking you in 38 here to determine the force of tension in the rope supporting the leg. The tension is going to be the same all throughout. It doesn't matter that it's weaving and weaving this way. So it's basically the leg here is weighing it down, and the force here. This is kind of the other thing realizing here. Yes, there's a force of gravity down of the weight there, But because this is stationary, this is another example where the sum of the forces equals 0. So if the leg isn't moving down, then that means that the force here is the same as the force there, which means that that is the tension. If his leg was going up or down, you'd have acceleration, but that's what took me kind of forever. And if you figured that out the first time, awesome for you. But these are not moving, so that means that equals that, which means the tension is going to be a 78.4. The other part took me a day and a half because I was just overcomplicating it here, is that we got a 105.2. Where this came from, it's asking you, and I had troubles, what is the traction force exerted to the right on the leg? Basically, what's that saying is that this person's foot is strapped into here and is pulling back his leg this way. Okay, so it's pulling back the leg this way, or it's pulling the leg this way, but Newton's third law, it's also, it's the contact between the foot and the plate are the same. So if we can figure out how much total force is to the right, then we can figure this out. And so we have, this is 78.4, and this is 78.4 here, but 78.4 cosine of 70. So we know the tension of the rope is 78.4, but we're wanting to know totally this way, what is it? So write 78.4 plus 78.4 cosine of 70 equals 0. And so the total force pushing this way is 105.2. And so the total force responding to that is also 105.2. So yes, so that wraps that up. I'll go ahead and put this back up here again so you can see it. Make sure I get home so I can watch the football game. They're playing Zionsville today. So that wraps that up. I appreciate it. Once again, Wednesday, it takes a long time for me to do this. I've been doing this. This is basically 2 hours right here. So I'm going to be putting this up on the Schoology page, but I'm also going to be putting it up on the YouTube. So I would appreciate, not for trying to get subscribers, but if you do that, what it does is it puts the more subscribers I have, when people search these questions, mine will pop up, and I will help more people rather than other ones that you may have looked at that may be more confusing. So I'm going to go ahead and wrap that up. I'll likely get these up, let's see here. I guess it's on me to get it up today, so I'll spend some time getting it up on Schoology and maybe not YouTube, but Schoology. So I'll go ahead and sign off, and I'll have a good weekend.